Now let's take a look at derivatives of exponential functions and also how to use chain rule with exponential functions. We'll start with the one that's relatively straightforward. Derivative of e to the x is itself. It's actually very easy to do, one of the easiest functions to remember. So again, derivative of e to the x, if you recall, e is 2.718 and it keeps on going. It's a constant. Which comes up quite commonly in applications and so on. And there are some, properties that we'll learn about it. But again, definitely e to the x is the easier one. Now notice if we have other bases, like a to the x, other than e, we'll have a ln of a in addition to this. So it's basically, it's itself, a to the x, but then we have a constant times a ln of the base. Now notice, so it could have had a ln of the e, for example, which is the base, but the ln of e is 1, so it doesn't come into play with e to the x. Okay, here are some examples. Well, e to the x is very straightforward, but what about other bases? Well, let's say y equals 3 to the x, and sometimes we'll write a ln of 3 in the front and sometimes in the back. It really doesn't matter, but I think of it as 3 to the x itself, and then times a ln of 3, a ln of the base, which is 3. And same idea, y equals 5 to the x, the y prime would be a ln of 5 times 5 to the x, or if we can also have the equivalent, 5 to the x times a ln of 5. Okay, and again, sometimes we put parentheses around the whole thing, sometimes around the 5. It's really all the equivalent expressions, just so that we know. Okay. Chain rule is going to be very important for us because a lot of times the exponent is more complicated than x itself. Like it could be some other function besides the x. So the chain rule would be just like chain rule works. If e to the x is outside function, let me actually write this. So if e to the x is outside and f of x is inside, so the exponent is the inside function. How do we do the derivative? Well, let's build this. Again, I do not recommend memorizing these equations because there's a lot of them. But how you build this is, remember how we take the derivative of the outside first, which is e to the f of x. Well, remember, it's itself. So it would be e times f, e to the power of f of x. So it's exactly the same thing. So this would be the derivative of the outside function. Then times the derivative of the inside function, which is f of x. So how we denote it is f prime of x. So this is how we build this, or this is how I remember this rule without necessarily looking this up. So let's do some quick examples with just e before we do other bases. So if we had y equals e to the 4x, let's take a look what the derivative looks like. Well, we have e to the 4x itself times derivative of the exponent, which is 4, and we can also move 4 to the front, so we'll have 4e to the 4x. And let's take a look at another one. So what if we have y equals negative 16 e to the 2x plus 1? Well, it works the same way. Negative 16 is a constant, so we just bring it down. Then the derivative of e to the 2x plus 1, that's what we focus on. Well, it's itself, e to the 2x plus 1, times the derivative of 2x plus 1, which is 2. But note, we have something to combine here. So negative 16 times 2 is negative 32 e to the 2x power. Okay, and likewise, the third example, y equals e to the x squared power. Same idea, the derivative would be e to the x squared times the derivative of the exponent, which is 2x. Which also becomes 2x times e to the x squared. So again, relatively simple once you get a hang of it. Now sometimes we have other rules, just like a product or quotient rule to use with exponential functions, or later we'll use log functions. Works the same exact way. Notice how we set this up. First, the derivative, the denominator is the square of the denominator, so which is x squared. Then we proceed taking the derivative of the top, which note how derivative of e to the x is itself e to the x. But what about the derivative of e to the negative x? Well, if you recall, it would have been plus e to the negative x times derivative of negative x, which is negative 1. This is why it becomes a minus. Minus e to the negative x. Times the original bottom, which is x, minus derivative of x, which is 1, which you can write or not, times the original top function. And one good thing about it, not much we can simplify here. So this is what we have. So you can have this 1 or not, but this is all you can do. Okay, now let's take a look at the chain rule of other bases. And again, we build it exactly the same way. If a to the f of x power is the outside function, then we have, if you recall, a ln of the a times itself, a to the f of x. So this is the derivative of the outside times derivative of the exponent, f prime of x. So really the only difference is a ln of the base. Otherwise, it's very, very similar. So let's take a look. Y equals 7 to the 3x plus 1 power. How do we do the derivative? Well, it's a ln of 7 times 7 to the 3x plus 1 power times derivative of 3x plus 1 is 3. And sometimes we can move 3 to the front, make it a constant. So this would be the final answer. 3 times the ln of 7 times 7 to the 3x plus 1 power. Okay. Now let's take a look at another one. Y equals 4 to the negative 5x plus 2 power. Again, base is the 4. So the y prime is a ln of 4 times 4 to the negative 5x plus 2 power itself times the derivative of negative 5x is negative 5 and 2 goes away. And again, we can bring negative 5 to the front. So that's how we do that. Okay. Let's do maybe one more example. Y equals negative 10 to the 3x squared minus 4 power. Again, the base is 10. So negative is a constant. So we keep it negative. And then we have a ln of 10 times the function 10 to the 3x squared minus 4 power times the derivative of 3x squared, which is 6x. And again, negative 4 goes away. And again, we can bring 6x to the front. Remember, negative stays, but the 6x comes at the front and the rest just kind of follows. And that's the final answer. And that's it.